next part of exercise a02 is going to have us use pointer arithmetic, actually, and addition of integer value to pointer to iterate over an array. So this is really a classic programming pattern, if you will, with C, arrays, etc. Let's start by the outcome of this part of the exercise. This is what we want to see on the screen. Okay, we want to iterate over the array, display the number of the iteration, display the content of a pointer p, which is going to be initialized actually to point to the first element of our array, and then display star p, which is dereference p, and therefore displays the content of this particular element of the array. So the code to do so is going to be extremely easy. I'm going to try to illustrate the two ways that you can initialize p to point at the beginning of your array. So here's the code. We have here the first way to do so. P is assigned array, I is assigned 0. Okay. Then we have our classic loop using I to iterate over our array. We increment I at the end of each iteration. We increment P at the end of each iteration. So what I want to draw your attention to is P++ means P equal P plus 1. So we add 1 to the address inside of P, which means we go to the next element of the array. So it's like adding 4 in this particular platform, since each int is coded over 4 bytes. Here, P equal my array, that's one way to actually initialize P to point at the beginning of the array, because my array, the name of the array, is by definition equal to the address of the first element of the array. So here, instead of writing my array, I could write address of element 0 inside of array my array, and that will be exactly the same thing. The printf here is trivial. Okay, there are a couple of tabulation here and there to make the output a little more readable. So I display the number of the iteration, which is index I, then the content of P, then the content of star P. I dereference P, and I display the content of one of the element of my array, so one that P is pointing at right now. Let's make sure this file is saved, and let's move on to testing it. And you see the results of the previous execution here. Compiles OK, a.out, and once again the address are changing, so we can refer to the first printf that we have in our code. These are the address of elements 0, 1, and 2. I go back to my loop. It's the same address I used, one after the other, so P is incremented correctly, and the content of P, what is referred to by P, is actually 1, 2, 3, which are the value I initialized my array with. So what is the meaning of adding 1 unit to a pointer on int? Same thing than removing, subtracting 1 unit to a pointer on int. That modifies the address containing P by 4 bytes, the size of an int. So that allows us to move forward and backward in an array. Now, modify your code so that it now works on an array of doubles, initialized to 1, 2, and 3, instead of an array of int. So instead of modifying here directly the array, because that's going to force me to change everything here, I'm just going to real quick declare a double. I'm going to call it another, just another, okay? And I'm going to initialize it of the same size, define it, sorry, of the same size, and use an initializer by end here, which is going to contain 1.0, 2.0, 3.3. Okay, now that I have this, I can try to do the same little experience. I know that this code is working, so I'm going to simply put this code here, put a printf before it, which is going to say /t, working on an array of doubles instead of int. And I'm going to now put another \n here. Well, actually, that's not critical. I'm going to just make sure that this is initialized to point to the array hanover. Everything else makes sense, except that P is going to have to be modified to P2, and I'm going to have to declare the variable P2, simply because P is a pointer on int. I cannot make it point to elements of type double. So I will have here another definition, double star P2, and this time I should be ready to compile this code and test it. So I'm going to make sure it's saved. Go back here, GCC. Little warning, line 41, int format double argument. Let's go and check what's going on here. Okay, as you can see here, the problem is actually when I dereference our pointer P2, I'm still displaying the result as an integer. So I'm going to change that into %lf so we display the result as a double. Let me save this file again. GCC. This time it's correct. Let's look for the a.out. There we go. So first, the iteration numbers are correct. The star P are correct. 1, 2, 3. So I'm iterating over the right array. Now, this is where my array starts. Element 1 is at address something 30. 38 is the next one. 38 and then 40. Don't be fooled. This is not the difference between 38 and 40 in hexadecimal is not 2. Okay? Remember that you go to the digit 0 after going through A, B, C, etc. So the lesson here is that between this address and this address I have 8 bytes. Between this address and this address I have 8 bytes again. So when I increment a pointer on int, I increment by 4. When I increment a pointer on double, I increment by 8. Well, that's making sense because the size of a double is 8. So everything that we saw previously about the difference between two int pointer, subtracting an integer value from an int pointer, adding an integer value from a to an int pointer, applies also to double pointers. But of course, the size of an int is different than the size of a double. So the outcome will be slightly different. So this is what this question here was prompting you to reflect on. And with this, we are pretty much done with this exercise. So I'm going to put back the code and stop this video.